Hi, glad to see you here. So we finished last week by talking about all the structures in a cell. Essentially, this was cell anatomy. But we need to do more than that. We need to understand some of the key processes that go on there inside a cell. And that is what we are going to do this week. We will start this first part of our module by considering what is energy. And there are a lot of energy-related jokes, but we are going to be a little bit more scientific than these here. So what is going to be our definition for energy here? Well, most introductory biology textbooks, including the one that we are using, define energy as a capacity to do work. And that is true. Energy makes things happen. And if you're happy with that definition, that is great. We shall go with it. However, for those of you who are wondering about it, I do want to make a point that I am not completely satisfied with this definition. And the reason is that sometimes we do have energy and it may not be available or accessible, if you wish, to do work at that very moment. But it nonetheless is energy. So just the potential to do work is enough. It does not need to be able to happen there and then. But since your textbook says that energy refers to the capacity to do work, we shall go with that. So all the energy in our life ultimately comes from the sun. Remember, we discussed this on our first chapter as we talked about the flow of energy through the ecosystem. And energy was these red arrows in this figure. In addition, we remember that energy gets converted all the time from one form to another. You remember, for example, solar energy is converted into chemical energy in photosynthesis, and then it may be released as a movement when we use sugars from plants to drive our body processes and mobility. But also remember that each time that we convert energy from one form to another, we lose some of it. And usually this is lost as heat. Okay, there is two types of energy, and I mentioned these in our introductory video. Let's have a look of those. So these books on this shelf hold something that we call as potential energy. Think about it. Everything on the Earth's surface tries to fall downwards because of the gravity. And therefore, when you lift books on a shelf, you are putting in some work and lifting them up from where they would naturally want to be. Therefore, there is some amount of energy stored in these books. Anyone who has helped a friend to move into a high-rise building knows how it takes energy to lug all that stuff up to the top floor. So that stuff there on the top floor holds now energy in form of a potential energy. Okay, so if potential energy was energy that is stored, what is kinetic energy then? Well, that's it. It is the energy in motion. When these books now fall from the shelf. In my example of the introductory video, this would have been the marker flying through the air. So these two are important. And I think your textbook uses an example of the diver that we see here. So we can measure energy in many ways. And in terms of the food, we often talk about calories. And I often ask my students, how do we know how many calories there are in different foods? There are these all kinds of comparisons that you can find about how much calories certain alcohol drinks or foods contain, and sometimes you see them compared as if they were converted in sugar cubes and so on. I actually have a rather cool video about contents of Nutella spread into optional materials at the end of this module. You can check it out if that interests you. And for anyone who is wondering what is the best alcoholic drink to drink if you are on a diet, well, I would say that sharp drinks like vodka, tequila, and so on are pretty energy efficient choices. But really, that is not what I want to teach you. The big question that I keep asking from my students is that how do we know that this and that product or ingredient contains this many calories? And often I get told by the students that there are these tables that you can use, that this many grams of this and that contains this many calories. And that is true. But how did they make those tables? Well, this is one of my favorite lab equipment, and I have some background in nutritional sciences, and most universities where I have worked have had these. But unfortunately, we do not have one here. Otherwise, I would have taken you with me virtually to the lab and shot a video to demonstrate how it works. But we can do it even in this way. So what you can see is that it is a big box, and there is a lid that comes up, and something can be put inside it. And actually, what is put inside is this metal jar on the right-hand side. In addition, there are all kinds of buttons and a screen. So let's figure out how it really works. So there are 6 or 7 parts to know, depending on how you count. And we will go through them, but I do want to say at this stage that this is one of my favorite questions to ask from students in tests. Basically, I ask them to draw it. And it is not about your artistic abilities, but whether I can recognize that you have included those parts that I was looking for. So let's have a look of it. First of all, we take a piece of food and put it into this small jar, known as the bomb cell in this figure. And we bring 2 electric wires into this container, which we use to ignite the sample of food. And then this jar is inside another bigger container that is filled with water. Why do we do that? Well, when the food sample burns, it releases energy which we can capture in this water as a heat. And we want the energy to spread in this water evenly, so we have small propeller in there to mix it. And of course, we can tell how much temperature of the water did rise by having a thermometer in there. It's really not that complicated, is it? Well, the beautiful thing about knowing how bomb calorimeter works is that it gives us a definition of a calorie. And that is, 1 calorie is the amount of heat required to raise the temperature of 1 gram of water by 1 Celsius degree. And since we do know how many grams of water we have in this apparatus and how much temperature did rise and how much food we put in, we can do the maths and calculate the calorie content of a food sample. It is pretty cool, isn't it? Do not worry, I will draw the pump calorimeter with you on the next item on this module. But I hope that this helps you to see how did we come up with this definition for calories. And of course, often these values would be so huge that we talk about kilocalories. Well, I want to introduce you to 2 laws of energy. And I know that unless you love physics, this sounds like a real pain, but I promise that they are really simple and intuitive. And in fact, We have already seen those. So the first law states that energy does not magically appear out of nothing or disappear somewhere that we cannot trace it back to. Instead, if you think of an equation, energy always has an origin that it comes from, and it has a destination that it goes to. Now, that wasn't too bad, was it? And the second law is just as easy. As we change the form that energy takes, remember, these were, for example, solar, chemical, movement, potential, and so on. Each time that we change the form of energy, some of it gets lost. And usually it is as heat that we lose it. That wasn't painful. Well done. I do want to talk about one more concept before we wrap up this section, and that concept is entropy. And you might be like, oh my, that looks like a lot of text. But stay with me and focus only on what is essential if this feels otherwise overwhelming. So entropy is defined as the relative amount of disorganization. And everything in the universe eventually leads to more and more disorganization if we do not put any additional energy to building up organization. The way I recommend my students to think of this is to think about your home and cleaning. Not many people love cleaning and organizing things at home. Some do, but most don't. So a messy room has more entropy. Remember, entropy was defined as the amount of disorganization. And in this case, we have a high amount of disorganization. So we have a high amount of entropy. And the opposite situation would be where we have little entropy. So little disorganization. And the picture on the left would be an example of that. Now I want to finish off by telling you why we do not teach about entropy until you get this far in your studies. I love this cartoon. So this concludes this talk. And remember that I have next a time-lapse video for you where I draw the bomb calorimeter with you. Who knows, you might need to do it sometime in the future.